Hi, thanks for coming. My name is Yuji Takubo. I'm a PhD student at Stanford Space Rendezvous Lab. Today, I would like to present Agile Tradespace exploration for space rendezvous mission design via transformers. This work has been a collaboration between the Space Rendezvous Lab and then also the Systems Lab in Stanford under the collaboration of Center for Autonomous Aerospace Autonomy Research, CSER. So to begin with, autonomous rendezvous capability in space has been unlocking many applications in space, from formation flight, rendezvous, proximity operations. There has been many works on the case-specific geometric or analytical formulation for solving a general guidance problem. Yet there has been increasing need of providing a general safety-aware trajectory optimization capabilities or trajectory generation capabilities in order to achieve more complex proximity operations in the future. Because those safety or sometimes dynamics are generally modeled as nonlinear or non-convex constraints, we need to solve some non-convex feasibility problem, at least ideally non-convex optimization problem. So one way to solve this problem is sequential convex programming, which has been increasingly popular in the aerospace control domain. It is highly generalizable, and then consideration of various constraints is possible via formulating the problem as a direct method, which means direct parameterization of the state and control actuation. And also there has been many theoretical works on convergence recently. However, there is still remaining gap between trajectory generation and non-convex problem versus what we really want to achieve in the rendezvous mission. One is the mission design aspect always is a multi-objective by nature of it. For example, to run the SCP or trajectory optimization problem, you need to find the final relative orbits or final transfer time, which is somewhat manually defined by mission designers via iteration. And then this is pretty much a heavy burden in the current mission formulation. And speaking of bringing it back to trajectory optimization context, recently there has been a tide of adopting learning-based method to enhance trajectory optimization capability, in particularly when using direct method. And this is so-called warm starting. In a sense, you can provide a good initial guess to the non-convex optimization problem, which is generally hard to solve, so that we can expect a higher rate of convergence or even getting a better optimality at the final term. One of the work we have been working is called ART, Autonomous Rendezvous Transformer. This is a transformer-based autoregressive trajectory generation architecture that I will present in a minute. And we have been looking into multiple possibilities to adopt this framework. So when you say trajectory generation, there are mainly two types or applications we are thinking of. One is offline mission design or operation art level, and then the other is more onboard autonomy. Means you want to execute some low level control. So we started with open loop deterministic framework for this, and then this has been evolving over the last 3 years into, for example, inclusion of a robustness by chance constraint past safety in a rendezvous context, which is extremely important operational constraints. Or we incorporate it in the MPC framework, which achieved closed loop control scenario. Also, more recently, we have been looking into using this transformer architecture and then concatenating it with a language embeddings. We are enabling the semantic trajectory generation and then associated reasoning capability as well, which is highly precious in the context of on-orbit reasoning for future autonomy system. This work is particularly inspired from one of the work which does a generalization of the trajectory generation using some various parameterization. And then as an extension, we are now thinking of, can we do some multi-objective trade space analysis? Imagine you're a mission designer who wants to build the rendezvous mission, and then maybe you want to do some trade-off of fuel, time, radiation, etc. And then we are thinking that this architecture also fits with this type of urgent need in the agile mission trade. So the problem statement we would like to present, we would like to talk here is, how can we unlock the capability of an agile multi-objective trade space analysis? So we call this a mission design, leveraging a trained neural network that is generalized across a wide range of problem scenario. What if we could generalize this trajectory generation capability across like orbital elements, or like flight time, or like various other like constraint configuration, so that once we put the input config file, we can generate a multiple solution like all at once in a significantly faster pace than traditional non-convex optimization based solver, which takes like usually a lot of time. So today, we would like to present the transformer-based trajectory generation framework for multi-objective trade space analysis. The key enabling factor of this research is like one, generalizing across multiple modalities with respect to mission scenarios. Particularly, we're going to talk about the mission specification across like flight time, and then also like chief orbital elements, including some eccentric scenarios, which is pretty hard to generalize in a traditional framework. Another one we are like introducing is an idea of like using a batched inference. I will like talk more detail, but essentially when we do a machine learning training, we usually have a batch training, which means like we stack the information and then get average of it and then do like gradient descent. Using the similar architecture, we can just like batch different initial seed and then propagate all at once so that we can efficiently compute multiple trajectories at the one single shot inference. That enables us to essentially provide a Pareto front of like multi-objective trade space. So to get in, we would like to first introduce the problem formulation that we want to solve. This is generally solved as generally formulated as like an optimal control problem in a discrete time. This is something like I hope you're already familiar with, but the objective is to minimize some objective function with respect to discrete time dynamics as well as state and control constraints. So this is a objective optimal control problem, but what we are interested in here to solve is multi-objective optimal control problem. You can see that there are many objectives like expressed here. And then the goal of this problem is to generate a Pareto front of like this problem. And naive solution, one way to do this is like fix one objective as a like weighted sum of like these m objectives, and then like solving like many non-convex trajectory optimization. That is like a naive brute force approach. And what we want to ask here is like, can a trained model capture the underlying trade-off of like this structure by like feeding a lot of like feeding a diverse data set of trajectories. So to enable the to generate a model, generate a trajectories across various modality from the learning-based method, specifically for transformer, the important thing we are introducing is like a particular trajectory tokenization. Namely, the trajectory generation process is transcribed as like a sequential prediction, which is like somewhat similar to how ChatGPT or other LLM works in a modern world, which is conditioned on the text. This is like a typo actually from the stages. The sequence prediction conditioned by the goal or constraint or more like like past history of trajectories. And then we would like to predict the one next step, what is coming next as like optimal control, or what is coming as like next state as a result of dynamical propagation. So there are mainly 4 steps of like our autonomous rendezvous transformer or ART workflow. The first 2 steps are what is called preparation. So we offline train them. And then like the next 2 steps is like deployment, which means like we are mainly like using it for inference for like our need. The first one comes from like a dataset generation. The fundamental principle of like ART is using a behavior cloning or imitation learning architecture. So we need to collect a diverse set of like good trajectory candidates. And then it is also important to diversify the domain that we would like to cover. For example, boundary states or like flight time. Using this domain randomization, we collect the sample trajectories using SCP, sequential convex programming. Then we perform a supervised training using the generated trajectory so that the predicted next control and predicted next state that is conditioned from the previous histories of trajectory tokenization that we discussed earlier as a like least square fitting. Once it's done, we are ready to deploy this model. How we're going to do it is like to do a batch inference. In a similar way, we do a batch training in the part 2 of the framework. We do like we feed multiple trajectory seed to perform like a multiple trajectory generation at the same time. Here, particularly, we use like a well-known dynamics that we are usually available in guidance so that we perform what is called dynamics in the loop. That enables us to generate a dynamically feasible trajectory all the time, which greatly helps like accelerating the warm starting of the SCP because like we are already satisfying one of the like big constraints that we have a headache. And finally, this is an optional step. We solve like a refinement phase using SCP. The important thing is like at the stage of like 3, after only transformer inference, the solution is like pretty similar to like what we would get. So like we can already achieve a great acceleration, but let's say like after seeing this trade-off or like multiple like objectives, maybe we can pick one of them. And then like at that point, we can trigger the SCP to finally get like a feasible solution out there. So that accelerates the mission design phase. So this like architecture is like tested against like 2 scenarios for LEO, low Earth orbit, mid-range rendezvous, and then second one, elliptic orbit, far-range rendezvous. Especially the second one, elliptic orbit, far-range rendezvous, is like pretty difficult because like we are now trying to generalize across like various orbital regimes. More specifically, we are thinking of like a low Earth orbit, like roughly like same major axis of like 6,500 meters to like 11,000 meters. This is a little bit like less than MEO, essentially. More importantly, we are trying to generalize across various eccentricity from 0.001 to 0.35. 0.35 is pretty aggressive elliptic orbit rendezvous scenario. And then to enable this, we introduce like what is called elliptic relative orbital elements, which is an integration constants of the Yamanaka-Anderson state transition matrix. And these like trajectory generation dataset complies with like minimum fuel across like different set of final time. And then like also like these trajectories are satisfying the safety constraints. Here, the safety constraints are formulated as like a chance constraint, passive safety constraint, which means like you're outside of the keep out zones like safety area with a probabilistic margin, even under the sudden loss of control. So this is very conservative probabilistic formulation that enables us to like perform like a nice connection to the actual navigation analysis we are doing at the stage of guidance. So this is like some like data set selected 100 of it. The left one is like LEO scenario, and then like the right one is like eccentric orbit scenario. You can see that like even like we are starting from like a lower energy state, the eccentric orbit has like some like swirling that is like not really like observable in the LEO scenario, which somewhat like indicating like the difficulty of like securing the passive safety from the traditional like relative orbit design in the elliptic orbit. So when it comes to like the batch inference for this specific case, we have like 6 elements that comes into the trajectory tokenization. Particularly what I want to emphasize is like we introduce like observation vector as like one token that is like conditioning the future trajectory generation. And then here we particularly condition on the target orbital elements. What is important is like what the transformer generates as a trajectory is conditioned on the target orbital elements so that they can generalize across them once we like condition that once we feed the information about this like debris or like the target we are chasing for. And also the reward signal that we are like conditioning has like 2 objectives. One is like a flight time, and then like this is conditioned as a remaining flight time in particular to show like how much time we have left. And then also the fuel is like introduced as another reward signal as well. So to summarize the workflow of the batch inference, we give a single boundary state. So you're starting from like a particular relative orbital states, and then also like particular chief orbital elements. That is like what we want to like do a rendezvous with. And then we set a range of like flight time. That is like the input. Then like this will be like recursively like recursively fed into the transformer framework that batch generates the trajectory. This results in like B, we are using B, but like B separate trajectories that also like naturally leads to the priority front because like it captures like different flight time, and also it results in different fuel consumption. So this becomes like something like this. You can see the trade-off of like, like delta V and then also time of flight. And we have like multiple options of like approaching to the target to reach this like rendezvous mission. And then finally, we can like on demand refine this like particular solution. For example, if we see like this trade-off, and then we can just like find, oh, this is interesting. And then that's the time we can do SCP. So this is like a demo I'm like presenting here to show like what is happening clearly. We are like feeding one target orbital element, and then like service are like relative states defined as shown. And then you can see that from here, like six different like trajectories are generated with like different arriving time. You can see like some of them are arriving earlier than the other, and then generating like this like Pareto front that approximates like somewhere in between the convex relaxation and then also the true Pareto front that you will obtain by solving like SCP recursively. What is important is like summarized in like actually bottom left figure that indicates the runtime of it. The important finding here is like compared to naively sweeping the SCP, the batch inference of like trajectory using GPU is like significantly faster and then like relatively compatible with solving like a same number of like convex optimization in the numerical based on the direct method. So this acceleration is like strong like confident booster for us that ART can generate multiple trajectory at the same time that is aware of like passive safety constraints, which is not capable of like implementing so in the convex relaxation problem. So I'm going to skip the second one. So this is a demo. And then, of course, like we would not want to like finish here. We would like to know like what is actually the statistical performance like of like this proposed framework. So there are two key questions I'm going to address. One is like about generalization. Can ART reliably generate high quality trajectory across varying flight times and diverse orbital dynamics? This is very important to ensure that generated trajectory that I showed here like earlier is actually something like respecting, for example, constraints or like something we queried as like a flight time. Another important question is like, is this like generated Pareto front actually accurate or more accurate than like the convex lower bound? This is also very important because like in that way, we can show that ART, the proposed method, is actually doing a better job in terms of like approximating the ideal solutions like Pareto front. That is like otherwise like not possible to obtain. So the first experiment about the generalization, we trained for the elliptic orbit rendezvous scenario using like a diverse set of chief orbital elements. And then like we tested against the space track orbital debris data catalog as shown here. So you see many diversity in the like 6 orbital elements. And then we sample like 2000 like test scenarios to check whether these like rendezvous is like going pretty well. And the results are summarized here. The 3 key metrics of like the SCP when we feeding it is like whether they are like going to feasible solution, whether they are converging in a better optimality, and then like whether they are solving fast, which means like are they like consuming less iteration in the SCP overall. And then the results show that compared to the naive like worm starting method using convex optimization, that is like basically solving a 2-point boundary value problem, initializing with the proposed architecture of ART generates like consistently lower unsuccessful rate, which means like we have like a higher success rate in the SCP by worm starting with what is generated from ART, with like comparable optimality and iteration counts in the SCP. So which is a good sign that we are generalizing across various flight time and also like orbital elements. And then the performance is like better than basically convex relaxation. So to address the second question, can we actually approximate the Pareto front better than the convex lower bound? This graph shows like the error between the like SCP's like objective at the very end versus like the cost that is like generated by ART and then like the convex optimization essentially. The gap is like the key part. And then essentially what this graph says is like, as long as you're in the orange part, as you can see, the ART is predicting the better cost. The ART is predicting cost that is closer to the true SCP cost that is like resulting at the end of the day. And you can see the distribution trend across like these like 3 cases that like although like for the solution where the CVX and the SCP cost is like almost the same. There are some like like distribution going here, but as like the gap between convex optimization and then the SCP solution gets like larger, then we can clearly see the ART cost prediction is like outperforming the cost prediction of like the convex baseline. So that also like endorses the fact that the proposed method is like becoming a more accurate Pareto front generator than the convex baseline. So in conclusion, we proposed a learning-based agile multi-objective train space analysis by leveraging the capability of autonomous rendezvous transformer. This is particularly enabled by the generalization across the flight time and then also target orbital elements. And this is applied to various orbital rendezvous scenario, in particular elliptic orbit rendezvous with like chance constraint passive safety, which is pretty difficult to generate. And this application of like we apply this framework to the mission design context. This is pretty new in the current field of like learning-based trajectory optimization. And then we demonstrated that this has a very good affinity to predicting the multi-objective trait space analysis, which can potentially drastically accelerate the entire mission design process, which is usually laborious and iterative and takes a long time. Future works include interplanetary applications. I'm very curious like how this performs well in a more nonlinear context. And then also like generalization across more mission parameters, for example, including sun exclusion or occlusion or like changing radius of like the keep out zone sphere. Those are pretty interesting direction to chase on in order to provide a like more versatile mission design tool. Thank you so much.